Okay, let's get started. So last time we started talking about the string duality, and then let's see. So 2A, I don't know, it's how many times we draw the picture, but repetition is mother of learning. So this is, they're related what? 2A and 2B are related what? T duality. How does type 1 and type 2B is related? Orientable projection. How HO and I are related? S duality. S duality. And then how they are related? HE and E88 and SO32 are related. T duality. Good. That's what we saw. And there is some 11D Sugura. Okay. Then so those are relation. And then okay, so that's what we have learned. Essentially, so these are we can see from the supergravity side and so on. And then, so if you just to take the 2A in GS goes to infinity, you get the M theory. M theory, this is 11D. This is 10D. So that's what we saw. And yeah. So what kind of brain does it have in 2A? What kind of brain? DP brain. P is even or odd? So even D2, D4, D5, D6. So ingredients is the like this way. And then here ingredients are M2 and M5. So directly M series circle, and then S1, and then this way. Anyway, so that's what's going to happen on S1, and this is KK momentum, and this is KK monopole. This is geometry. I just tell you a bit of lie. Last time on KK monopole, actually this is the circle complication, so it's okay. Taubnat. It's the circle complication S1 fibered, not cigar, sorry. Fibered over R3. And then at the origin, this so at the generic point you have a circle, but if you go to the origin, the circle vibration will shrink to the point. That's why you get the cigar. At the generic point you have, this is R3 and S1 vibration. So this is the whatever, the projection of this cigar. Projection of cigar is just line. Line. At the origin, it shrinks to this circle shrinks to the point. So this is becomes cigar geometry. And at the origin, this D6 brain will show up once you compactify this circle. That's the. And then the tension of this M2 brain and M5 brain is 2 pi over 2 pi L Planck length cube 2 pi LP to the 6. And then if you do appropriately the calculation, you can get the tension of the extended object in type 2A theory. So that's what we have learned last time. Okay, and then what was that? So radius of the M3 circles, S1, let's call M3 circle. So radius of M3 circle is indeed given by GS times LS, string length, so that it's proportional to the coupling constant of string theory. So if you take the large coupling limit, this 11D M3 circle is really become visible, because I mean the radius is really. But if you weaker couple regime, this S1 is shrink to the really tiny, so that you cannot see that effectively. Effectively, we cannot see that. So that's what's going to happen in type 2A. So M2 brane word volume theory. Of M2 brane. You might have heard of it. So Barker, Lambert, Gustafsson, and also Aharoni, Bergman, Jeffrey, Maldacena, 08 and 07 around here. They found some exotic Chern-Simons theory. I don't remember the date. Not date. Yeah, 07 or 08. Yeah, good. So some exotic. So the Born series, of course, this is 2 plus 1 dimension. I don't like. I don't want to separate space and time. So D is equal to 3, whatever. D equal to 2 plus 1 dimension. So exotic, supersymmetric, some exotic. Suzy, Chern-Simons, matter theory. So that's what they found. Barker, Lambert, Gustafsson, ABJM, and they just. I don't know. I mean, you might have heard if you take large n limit, so n M2 brane, if you take large n limit, so they also find the corresponding geometry, ADS4 cross S7 divided by ZK, K related level Chern-Simons of Chern-Simons term. So that's what we found, like a beef. This is actually what, anyway. When I was a graduate student, yeah, anyway. And then so around this M theory was constructed, the people already noticed, Witt and Seiberg noticed, so Ward volume theory, Ward et al. Ward volume on M5 and M5. Is called 60 supersymmetry. It's called n, 2,0 theory. So it's a chiral theory. So you have a left moving, actually supersymmetry, right moving supersymmetry. One can have in 60 superconformal field theory. And then superconformal field theory, if n is greater than 1, it has a so-called two-form field B, whose two-form field B. But this B2 is actually different from B2 in the string theory. this is not coupled monofield. This is essentially coming from anyway. So I will explain. So and if you take the field strength, I call it DH again, P23. This H3 is indeed self-dual. Self-dual. And then you have some spinors, psi alpha A runs full. This is satisfies some condition. A runs full. 1, 2, 3, 4. Four spinors. And unfortunately, I don't have a space to write down, so I move on to here. And 5 scalar. So 5 scalar. 5 scalar. Is it okay? Yeah, 5. Yeah, 5 scalars. Lurs. This is what xi runs for 1, 2, 5. This is essentially the M5 range, so the 11p, and the M5 range is the M5 range, bunch of M5 range, stack of M5 range. And transversal direction is actually the moving for transversal direction, so that you can just move the transversal direction. So Wahlbaum series is 1 plus 5 dimensions, so therefore 6 dimensions. So the orthogonal direction is 5 dimensions. So therefore, if you fracture the M5 range on the orthogonal direction in space-time, you get this. Essentially, this is the just will create a scalar field. So therefore, it's a 5-dimensional orthogonal dimension will create this scalar field. But so what is this two form? So the two form is indeed this M5 range, but M2 can attach on like this way. M2 brain. Okay. So this is so if you M2 brain, so this is 1 plus 1 dimension. This is 1 plus 1 dimension. So this attachment is indeed 1 plus 1 dimension, and this is called self-dual string. Self-dual string, because that will create a V2 field. Self-dual string. String. Let's go self-dual string. So string means because the space dimension is 1 dimension, so therefore it creates the two form, and whose field strengths satisfy the self-dual condition. So therefore, so this be the two form field. People call tensor field. Two form tensor field is indeed it is created by this self-dual, the M2 brain attachment M5, so of which is the self-dual string. And since you cannot have the kinetic term, so this is 3 form, this is 3 form, this is H wedge H3, and since H3, if you commute this one, this is the minus of H3 wedge H3, so this is 0. Okay. So if you commute H, 3 form, if you exchange this extra derivative, you get a minus negative sign. But unfortunately, so therefore, you cannot. This means that you cannot write field strength. How to say? Kinetic term for this self-dual string. So this means that so within Cyber already notice that there is no Lagrangian description. I think it's around I think 96 or 97. I don't remember the detail. Anyway. I don't. Most likely 96. I don't remember. Most likely 96. And so before you guys are born, right? Anyway. So that's why the 62,0 theory does not admit the Lagrangian description, and its class so it has a type so-called ADE, type G, ADE. ADE means that the A is corresponding to SUN, n minus 1. D corresponds to SO to N. E6, 7, 8 is the so-called exceptional rearrangement. E8 is already has already appeared in the heterotic string. But anyway, so this will be classified by ADE. Lots of things. So you cannot write a Lagrangian description. So it's kind of mysterious theory, but lots of things going on in nowadays, even and then lots of. Anyway, so for instance, if you put the M5 brains on S1, and if S1 shrinks to the point, this will give 5D maximal supersymmetric ambulance. Maximal is supersymmetric ambulance. People call n equal to 2 sometimes. N equal to 2. So this has a Lagrangian description. And 5 brains on Riemann surface with puncture. This is called for the n equal to 2 supersymmetric theory. The theory. People call it class S. Class S. So S stands for 6. The acronym was 6 because it's 62, coming from origin, coming from 2, 0. Anyway, so that's the. This is already Cyberg. This is Gayoto. 09. And so and then so people already studied lots of things and 3 manifold that will give you 3D n equal to 2. Anyway, supersymmetric theory. I don't know, Bukov et al. Many people still going on. Anyway, people M4. Anyways, 2D n equal to. Depends. 0,2. How to twist and so on. Depends on anyway, and so on. So therefore, if you're starting from M5 and wrap a compact file on some manifold, it creates a lot of interesting supersymmetric field theory. Anyway, so supersymmetric field theory mostly these do not admit Lagrangian. So generically, this theory, since parents do not admit Lagrangian description, so its cousin also inherits its DNA. So generically, no Lagrangian. No Lagrangian. Generically, no Lagrangian description. I mean, it's I don't know. I mean, it's anyway. Yeah, of course. I mean, there are lots of. Anyway, I'm not gonna go into detail. It's already a research topic, and then I'm literally working on this kind of subject. Okay, so that's the case. Now, okay. Unfortunately, I erased. So, Okay, so what is this relation? So we know this is the T oriented for ST. 2A, I mean, if you go to infinite coupling limit, and then take the low energy description, you get the 11D Sugra. 11D Sugra is a low energy description. M theory can be understood as M theory. Then how about the HE and then 11D Sugra is related? So this is found by so-called Hojaba, Witten. I don't know when, to be honest. Oh, this is 96. So we know that type 1 is 32 D9 prime plus 09. And if you put that on S1 and take T del, so we call it type 1 prime, which is 32, what was that? It's so 16, so it's 32 D8 prime plus 2 O8 minus on the segment. So according to the S1, and you put you put the 32, whatever. I cannot draw 32 here, but the 32. What I'm writing? Sorry. S1 and then so 32. 32 D9 brain, and then 09 also. 09 is here. 09 minus here. This will create SO32. And if you take TDL, geometry becomes segment. And here you have O8 minus and O. So if you take TDL, O9 becomes a pair of two O8 minus, and in between you have whatever 32 D8 prime. So that's a type 1 prime. Okay, so this can be understood as the 2B, type 2B. Type 2A. Sorry. Type 1 is in fact type 2B with orient 4 prime. So type 1 prime is type 2A with orient 4 prime on the segment. Okay, type 2. It's originated from type 2A. So we know that type 2A, if you take the infinite coupling limit, the 11 dimension will show up. The same thing happens for type 1. The same thing will happen on type 1. If you take the infinite coupling limit for type 1, the M0 circle will show up. So this one, if you take the infinite coupling limit, GS goes to infinity, and this will become so-called heterotic M theory on S1 cross S1 mod Z2. So this is S1 is M theory circle. So of course this is 11D. So this is M theory circle. So if you compactify on the heterotic M theory on the S1, you will get the type 2A. Okay, type 2A. Or type 1 prime. That's that type 1 prime. And what's happening is that they're really so segment. I mean I cannot draw, but so 11 dimensional. So this segment is literally so this is the 10-dimensional thing, 10D, and then this is S1 direction. My drawing. So this is the S1 mod Z2. And this is the 10-dimensional. So this is essentially whatever S1 M3 circle times what was that? I don't know. Say for simplicity 1,8. Okay, 1,8 for simplicity. Then we recall that this in between we used to, if you go back to the type 1 prime, you have a 32 D8 brane and 08 minus 08 minus. So it used to be here you have there's something going on here. So it used to be at the end of the segment you used to have the 08 minus, okay, 08 minus, but it just lifted to the heterotic M theory. And in fact, what's going to happen is half of them, half of 16D8 goes to the 16D8 goes to the one end of the segment. The other 16D8 goes to the other end. They form. So that what's happening is that they really here at the end you have 08 minus plus 16D8. 08 minus plus 16D8 on the hand, and they just lift it to the heterotic M theory. That will create so-called M9 brane, or people call end of wall, end of the word plane brane. And so this is a lift of 08 minus M theory lift on GS goes to infinite limit of 08 minus plus 16D8. Okay. So the other side you also have the M9 plane, M9 branes. Okay. M9 branes. Okay. And as you can easily imagine that the 08 minus plus 16 D8 will create naively SO16. So on the SO16 here, and here you also create the SO16 here. But this one gets enhanced, in fact. Indeed, it gets enhanced into the E8 enhancement. At GS goes to infinity. This is enhanced E8 to the GS goes to infinity. Okay. So therefore, there are actually 10D E8 Yamil theory living on the boundary. E8 Yamil theory, and 10-dimensional, and the 11-dimensional in between. Actually, there is some cancellation by anomaly. So the bulk theory has anomaly, but there is so-called anomaly in flow cancel with the boundary anomaly. So that's called anomaly in flow. I would, yeah. Anyway, so then if you compactify on S1 on Z2 and the GS goes to zero limit, you get the heterotic. As you can easily imagine on S1. So now, if you just compactify on S1 cross Z2, this direction it just shrinks to this direction it shrinks to the how to say the M9 branes actually meet each other. So this direction is now GS Yamels. Proportional GS Hamilton, and if you go to the weaker couple limit, they just, how to say, meet each other, I mean, by stacking. So that this direction will disappear, and it becomes 10-dimensional. And then since you have E8 on the wall, and the E8 on the other wall, and if you meet together, you get the E8 cross E8. So it's a magical thing that will happen when you go to M theory. So that's what's going to happen. Okay, so yep. So that's what's happening. So the upshot is that the so HO on S1 and then type 1 on S1 is related by S duality, and if you take T duality, you have a HE on S1, and here if you take a T duality, you have a type 1 prime on segment, and if you take the infinite coupling limit, GS goes to infinity, GS goes to infinity, you get the heterotic ambiguity. So that's what's going to happen. So that's upshot on S1 cross S1 set. And at the end, you have an end of the wall or whatever, Hojawa within domain wall, whatever you call it. That's what people call it. Okay, so that's the case. In the lecture note, I talk about the duality of heterotic T4 and the 2A K on K3 are dual to each other, but I'm going to skip. I'm going to skip this thing. Yeah. So then I'm going to talk about so-called Green-Schwarz anomaly. So this week I just spent a lot of time on writing the Green-Schwarz. So nowadays the updated overlay file has a new section of the Green-Schwarz anomaly cancellation, so you can take a look. It's not completed yet. It's just rough, but it's for today's purpose it's enough. Okay. So let's talk about the Green-Schwarz anomaly cancellation. So essentially, what was it? So this is here 11D sugra, and this is 10D. N equal to 1 super Yang-Mills with E8 gauge group, 10D, N equal to 1 super with E8. And then anomaly cancels. But in our case, what we are going to consider is so-called Green-Schwarz anomaly cancellation. Okay, so what is an anomaly? So what is an anomaly? Just consider Z of A, which is given by the E to the path integral, whatever, the phi, whatever, E to the minus S and phi. And then A can be understood the gauge field. Okay, background. Okay, background gauge field of the symmetry G. G can be anything. So at this moment, I consider the G as a global symmetry. At this moment, global symmetry. global symmetry. Okay, symmetry of the S phi. Okay, S is action or Lagrangian. S can be understood the dx Lagrangian phi. Symmetry of the Lagrangian. Symmetry. So okay, so it's a symmetry of the action or Lagrangian. So I'm not gonna talk about the symmetry of the path integral. And to do the gauge transformation. So gauge transformation is the, as you know, G inverse dg plus G inverse AG. So this is the symmetry transformation where G is inside the symmetry group G. Then anomaly is indeed at the level of path integral. There is some cost, some extra term we show up, e to the I a sorry, I mean maybe for infinitesimal version. So if you consider some infinitesimal version, G is equal to 1 plus epsilon, for instance, epsilon, then GA. So this part is called anomaly. So this part is there is some cost we show. This is called anomaly. So I learned that in Chinese anomaly, in Chinese is translated into Fanjian. But however, this anomaly is not that bad. Not something bad. It characterizes the theory. So it's a quantum theory. The quantum theory. It's one of the very basic information. One can study for the quantum field theory. So that's the lesson learned from Tooft. Tooft. 80. I forgot 7 or something. I don't remember. Question mark. Who tells you that this anomaly is indeed invariant under the RG flow? So therefore, even if you incorporate this all the quantum correction, this one does not change under the RG flow. So therefore, it characterizes a quantum theory. And moreover, so it is an obstruction. Obstruction of the gauging symmetry G. So here it's a global means the this whatever G is the global symmetry. So the gauging is G goes to G that depends on X. Is indeed this is not allowed if you have an anomaly. So then the gauge symmetry is broken. If you have an anomaly for gauge symmetry, theory is not well defined at the quantum level because it breaks the gauge symmetry, and many things will break down at the quantum level if you don't have a gauge symmetry. And since this alpha cannot be removed, so alpha epsilon is the essentially, so let's call this one is equals a d to I, right? This one is let's see, e to the, I don't remember, w. I don't remember then my notation. Minus, let's go minus side. Minus is the symmetry of the WA epsilon. And this cannot be removed by local counter term. So this cannot be. So therefore, it can be written as some m to n omega to n a epsilon. And this is somehow cohomological. So it knows about some the global topology of this space-time. So here, so in this section, we only consider even dimension. D is equal to 2n. Space-time dimension. This is space-time dimension. Dimension is even. So since this anomaly cannot remove by local counter term, it's more like it becomes really like know about some topology of the space-time with bundle. So bundle means the where the gauge field lives in the full symmetry. Cohomological or topological. Cohomological term. Okay. So essentially this can be understood as 2n form. 2n form. And there is a so-called powerful machinery called an anomaly polynomial. Which start from 2n plus 2. So this is the it's a homology 2n plus 2 form, and this so-called descent equation and the West-Zumino and West. It's a consequence of West-Zumino consistency condition. Consistency condition. We can obtain omega to n. Can obtain. Omega to n. So that's the starting from two-dimensional higher form. That is called anomaly polynomial. And use so-called descent equation. I will just briefly write down the I to n plus 2 is equal to d of omega Chern-Simons form, which is 2n plus 1. If you take the variation in terms of this gauge field, that will give you omega 2n. So this is called descent equation. Such a simple thing, and one can obtain the omega 2n. And this I 2n plus 2 can be written in so-called characteristic classes. Characteristic classes. Essentially, this is written by Chern form and also Pontryagin form class. So today I'm going to talk about this machinery. This is very powerful machinery. And then from then, I will talk about the problem anomaly of the sigma n equal to 1 sigma of type 1. So this is the algorithm. 83. So if you use this anomaly polynomial, you can easily find that there is something wrong in supergravity in any good one of type 1. And then 1 year later, so Green-Schwarz mentioned 84, mentioned if you add the d equal to 10, 10d super YAML plus add 2 pattern YAML, G is equal to SO32 or E8 cross E8. This anomaly cancels. No anomaly. So that's what the Green-Schwarz. Okay, so that's that. So let's start talking about this anomaly polynomial. So what is the source of anomaly? So when you learn quantum field theory, so the quantum field theory of standard model, when you learn, I think the most important feature of the the QFT you will learn is so-called beta function. Both QED, my personal opinion, QCD, be it beta function. The other thing you learned is so-called anomaly, ABG anomaly. And then of course here anyway. So okay, let's not talk about it. Okay, so ABG anomaly. So that this one is actually just learn this kind of. If you just compute this kind of diagram, so that's J mu. What was that? J mu 5, and then we know the 5 is indeed some number proportional trace f wedge f. So that's some number. I don't remember the number. In fact, you will get this anomaly. So this is conserved at the classical level. But if you compute this loop diagram, you will encounter some anomaly. And here, the important thing is this loop diagram. When you compute this one, it's so-called Carl-Fermin. So that anomaly is due to this kind of phenomenon, loop diagram, Carl-Fermin. What is the Carl-Fermin? So you start with Dirac fermion, but you can just define a gamma 5 divided by 2 and psi, and then so Dirac. And this is whatever chiral or Weyl fermion. And since in standard model, if you consider electroweak theory, so we know electroweak theory is a chiral theory. So left-handed fermion is different from right-handed fermion. That's who found this one? Do you know? Who found the electroweak theory is a chiral theory first? You guys should know. Yeah, and Lee. So this is the parity violation of the electroweak theory. So I don't remember, 50 something, right? 50 something. Anyway, and then she's experiment. I don't know. I don't remember how to. Oh, sorry, I don't remember how to write. But anyway, she experimented confirm that anyway. Party violation. Up. Ayo. Oh, intact. So anomaly is due to this chiral priming. So the anomaly is due to the contribution chiral priming. And then, so if you go to the higher dimension, d is equal to 2n. So this is d equal to 4, d equal to 4. D equal to 4. D equal to 2, and for instance, d equal to 6. Instead of triangle, you have to consider the chiral priming of the loop diagram of this kind of stuff. Square diagram, d equal to 8, it's become octagon. So you need to compute this kind of loop diagram, and d equal to 10 is the hexagon. So in the loop diagram, everything, all the anomaly is due to chiral priming. If the theory is chiral, you have to always be careful about. You have to always care about the anomaly. So for instance, when you say 62,0 theory, 2,0 theory. So it's already so this 2,0 means the left moving and right moving Fermi. So this is already chiral theory. So this left has a supersymmetry, right moving do not have a supersymmetry, which means chiral theory. So therefore, you have to be careful anomaly for 62,0 theory. The same thing happens. 2D n equal to 0,2 or whatever 0,1. This means that the left moving and right moving behave differently. In that case, you have to always care about the anomaly. Always there is some source of anomaly. So therefore, and also standard model too. The electroweak theory, left moving ferment, right moving ferment plays different role. That we already knew from this Yang and Lee. I think one of the most famous physicist in China tells us. Okay, so let's and then from this analysis, so the Western Zumino, and then also I forgot the Stoica. I don't remember. Sorry. Anyway, I don't remember the. Let me search. I think. Yeah, Stora Zumino. Zumino. Found that some like a top-down approach. It's top-down approach. To this anomaly. Without computing one left pattern. Without computing loop diagram. So that is called anomal polynomial. That I'm going to explain. Okay. so d equal to 10. So of course, let's first define the Carl Fermat d equal to 2n. 2n. Let's see. So the gamma matrix, you always have the Griffith algebra for Fermat to define. And then from here, Dirac Fermat is a representation of gamma I plus minus is given by gamma to I plus minus I gamma to I plus 1. And that will create a creation annihilation operator. And from here, you have a 2 to the n spinor representation. So that corresponds to Dirac Fermat. And of course, when n is equal to 2, 40, and 2 square is equal to 4. So therefore, in 4-dimensional, Dirac Fermat is a 4 component, right? Psi 1, psi 2, psi 3, psi 4. Okay, that's why 2 square is Dirac Fermat. However, if you define this psi is split into gamma, what was it? 2n plus 1 divided by 2 psi, where gamma 2n plus 1. I mean, this is always what's going to happen. 0, gamma 1, 2n minus 1. So this is a Carl operator. I mean, this one. And this, in fact, this 2 to the n is not the irreducible representation. In fact, irreducible representation is in fact the spinor, conjugate spinor, n plus minus 1. So it splits into the, this spans by psi plus and psi minus, and it's also called Carl Fermat, or some people call Weyl Fermat. And then we consider the path integral. So we consider path integral of this kind is equal to deep psi bar e to the minus d dx capital D. Okay, so there's a lot of state type of I d slash psi plus. So now it's a Carl theory. So we only consider the Fermat with positive chirality, not negative chirality, because I mean we only Carl theory we have to be careful about the anomaly. Now of course d slash you know, right? Gamma is this one. Gamma mu partial mu plus a mu. Okay, so that's what's going to happen. And the gauge transformation a mu is in fact whatever d mu theta of course partial mu plus a mu theta. Okay, so that's what's going to happen. So this is the gauge transformation. Okay, I mean essentially. Sorry, delta a mu is like this. So the a mu is transformed a mu plus d mu theta. That's how they by gauge transformation. Another gauge transformation. If it is a non-abelian case, we can just consider the a mu is and what TA is the generator of Lie algebra So does QFT2 tells us the ABG anomaly? Do you learn? Xiao Dingyu, right, recently. He doesn't tell it. Okay. Okay. Okay, then this is the good place to learn anomaly from different perspective. Okay. Okay, at the Fudan nobody tells the ABG anomaly. Okay, that's sad. That's pretty sad. But this semester the Gujain will teach. I hope he will teach. Anyway. And then under this transformation, oh okay. Oh okay. So you never did this computation. Okay. If not, I mean you should read whatever chapter 19 of the Peskin. So then another gauge transformation, this effective action. So this is called effective action. Delta W. Delta W is B or capital D or whatever. Is delta A mu of X delta W delta A mu A, and which is equal to ddx. We already know this is the W. Okay, and then the Miami sign. Theta A mu X. Sorry, I think what's the correct way of writing? It should be sorry, like this way. Okay, and then people usually call it this one. People usually call it this one is equal to minus d dx theta a d mu j mu a. So this way. This is and if quantum mechanically this delta W is equal to 0, you have a quantum mechanical conservation. Quantum mechanical conservation of the necessary. Okay. And then of course we know that so if you apply del A on this action, what's happening is that the this J mu of A is given by I psi W gamma mu dA psi. So as you can see, so delta A mu on this this path integral only see this part. This covariant derivative only has the A mu part. So therefore you just get rid of it. What's left is this guy. So this is the current of the this gauge transformation. Gauge transformation. Okay, and then if so, this means that if d mu j mu a is not 0, there is no anomaly. Serious anomaly. So let's rewrite this delta W in a slightly different way. we assume that we take the TA as a basis. TB, people just write down the A, B, C, T, C. I'm taking the Einstein convention, and this can be taken completely antisymmetric. Antisymmetric. Symmetric as the I may be wrong. Just a moment. Yeah, so I take that this is antisymmetric. So we can take such a basis as a TA. So let's rewrite this delta W as follows. This way. I mean, just rewriting. So this part is this way. I mean, we know that this is partial mu plus a mu, and which is written like this way, and then the integrable parts, and then using the antisymmetry F, we can just write down like this way. Like this. Okay, and then we define this part is this is the operator. This is the operator delta theta A theta A, yes, theta A of x. Okay, so if you do that this one, then if you compare upper bound and lower bound, what you get is the following. What you get is the this d mu, j mu. I mean, it's just simple manipulation. It's given by delta A, del theta A, x acts on w. So it's just a rewriting of what I have done over there into the like this. But now, so the Watson Zumino notice that this del theta satisfy the following condition. So it's easy to check that. So this del theta A, of course, because I mean it's just a del theta B x prime satisfy. If you take a commutator, so by definition, this acts on. I'm not going to go into the details. So the partial mu A mu plus F A B C A mu B del A C mu. So this one, and then you just apply the same thing on same thing on here. So then del A acts on here, right? Delta A acts on the next one, so you have the same term. Acts on this one, okay? What's left is FABC delta A. And you have to consider the some anti-commutator of A, B, and A, whatever, C or whatever, A, D or whatever. That will give FABC. And it's easy, straightforward calculation. This will give you like this one. Okay, so that's what you do. this delta A satisfies some kind of Lie algebra relation. So it's just a generalization of this guy. It's just generalization of this guy into. But it's of course because I mean it's just delta A is the variation, the functional variation of theta A, TA direction. And this is called and if you write down this one, it's like a GA. And they satisfy the following condition. Okay, whatever. I mean, it's just a straightforward application of this guy. Del theta B, GA of X is FABC, GC of X, and delta D, X minus X prime. It's just a application, this one on W. We'll give you this one. Oh, this is called what's seminal. Consistency condition. So anomaly, even if you have an anomaly non-zero, this is indeed equal to GA. This anomaly should satisfy some condition. Okay, so this is literally GA. Should satisfy this condition. So this is called what's the consistent condition, and this consistent condition constrain anomaly significantly. And without computing, so you don't know how to compute it because you don't learn it. But anyway, ABG anomaly computation is kind of involved, but without doing a one loop computation, by using this consistency condition, one can determine the anomaly. So that's I'm going to talk about it, but it's, let's take a break. 10 minutes break. Yeah, yeah, yeah.
Yeah, but
It doesn't work, right? Yeah, it doesn't.
But it's, what is it, much worse.
Okay,
It's
much
not associated. The most natural way of
Okay.
defining
Okay.
how it works.
Okay. Okay. I think then this direction is too hard. That's why people doesn't do not make for. Ah, yeah. Okay. So today is 8 p.m. right? Meeting. Okay. Hopefully I can make it. Yeah. Okay, so let's resume. Okay, let's get started. So now let's reformulate this with seminal consistency condition by using BRC transformation or BRC ghost. We introduced some rewrite. The with seminal consistency condition by BRC ghost. So when you so the shouting you tell you the this Fourier-Popov ghost. Okay, that's okay. Okay, that's, so the quantization, unless he did quantization, yeah. Okay, well, anyway, that's necessary, but he doesn't do that on anomaly. Okay. So we introduce so-called Grassmann odd. So which means Fermi C and TA, and we introduce delta BRC transmission CXB. So the CX means CXA means CAX. So just shorthand notation delta theta XB 8A del B CA minus 1 over 2 FABC CB CC. Okay. So let's consider it's just ad hoc, but introduce this. Then what's happening is the del B square A so A is given by delta B CXB del theta B X A and minus C BX del theta XB del B X. So it's just like this rule. So del B. So you just apply del B on this guy, and then del B acts on C, and del B acts on A, and minus sign coming from del P is the Grassmann odd. So therefore, when you pass del B, you have the minus sign. So del B by how to say the Grassmann odd ghost field, you have to have the negative sign. Okay, and then, so the first term, so this first term, let's see, this first term, I mean, if you applied this guy, you just plug it into there, is equal to minus R over 2 FABC CCX CXD del theta B of AA. Okay. And then if you use the secrecy condition of this guy, you get the F B yeah DBC yeah. Well, what I'm writing here? Not ABC, BCD. BCD. And if you do the secrecy, you get the CXB, CXC, and del theta dx. Yes. Secrecy, you have a. And the second term is indeed, and apply the first one into here. What you get is as follows: CXB del theta bx, CYC del theta cy, A. And then by using the CR Grassmann-Alt variable, if you swap the B and C indices, you get the minus sign. So therefore, this can be rewritten as the 1/2 CBX, CCX, and then delta theta BX, del CX, CA, CX, and A. Okay, so that's what's happened. So if you add them up with taking care of a negative sign here, what you end up with is as follows. So what you end up with delta square AA is indeed 1/2 CBCC XX and the minus ABC del theta XD. Is it okay? No, D. Yeah, plus delta theta BX and the commutator is delta theta CX and commutator and times A. So, and if you compare with this guy, so what's the consistency condition here? Rewriting for the proposed. And then if you apply here, we know this is it. So this is the, if you apply the for the BRC transformation B is indeed equal to 0 due to the with a consistent condition. So this blue part is equal to, indeed, corresponds to this blue part here. Okay. Therefore, this is equal to 0. So therefore, conclusion is this is really BRC transformation. BRC transformation. So if you just introduce this delta BRC ghost C, and if you define delta B like this way, one can find that this delta B is indeed equal to 0. Delta square is equal to 0 is equivalent to the West-Zumino consistency condition. So vice versa. Okay, so that's I think for introducing ghost. So therefore, so this looks a bit complicated, but delta B square is a way more fundamental relation. So it's better to use this one. So that's what was Zumino found. Yes. Okay. And then Stora and Zumino found a further simplification, further more thing. Okay. And we know that this delta W is indeed given by 2 pi plus some, we want to write down this is m to n, omega to n. So this is the, depends on A, depends on A, and C, and C. So this is a gauge transformation, the gauge transformation. Since we know the delta C square, C is indeed, I mean, delta B is involved with C, right? So the direction of C. So the involves, so I mean, is the, is equivalent. W of A and 2 pi m to n delta C omega to n, and C is equal to 0 because of the delta square equal to 0 condition. C is just a direction. So I mean, essentially, I mean, what should how should I explain? I mean, this is essentially equal to delta theta x b cb x. Okay, so that's what. And then I sometimes call this entire chunk is equal to delta C. So that's my notation. Okay, so because I mean it depends on goes C, right? Okay. And let's reformulate this one slightly different, more cohomological way or topological way. Suppose M to N is a closed oriented. Cross-oriented. So then there's some manifold, whatever. So this is M to N. And there's a manifold which is 2n plus 1 dimensional, which bounds the original manifold. Cross-oriented. Then this anomaly this anomaly can be written as delta WA can be written 2 pi by Stokes theorem to n plus 1 dimension, and then d omega to n is C. Okay, so it's just a Stokes theorem. I mean, so we extend all the field. So we know the field is living on 2n-dimensional manifold, but we extend to all the field to the high dimensional manifold. Okay, we extend, and okay, then we can just define this kind of 2n plus 1, and then we applied the. So then there was Zumino consistency condition. Condition is indeed now delta C1 and delta C2 acts on. So if you twice acts on the effective action, we get the 2 pi, and then M2 n plus 1 dimensional delta C1 d omega 2n C2 minus delta C2 d omega 2n C1. Okay, 2n C1. This is C1. And then what's the consistency condition will tell us that this is 2 pi, and then n 2n plus 1 d omega 2n. And then just commutate as C1 and C2. Okay. C1 and C2. So here is just a delta C and C1 and C2 are different direction of the lead derivative. Therefore, this is essentially will give you whatever f a b A, B, C, C, and then whatever, C, C. We'll give you A, B, C. Okay, and this, if you look at this, if you step to this equation, one would think that if you define this d omega, so one would expect that if you step this one, so there exists some omega, I call it Chern-Simons form, 2n plus form, independent of C, such that if you take the derivation gauge transformation along C direction of omega 2n plus 1, Chern-Simons is equal to d omega 2n. D omega 2n. So then this equation makes sense. So if you replace this one, it's equal to omega Chern-Simons delta C2 2n plus 1. This one you replace delta C1 omega Chern-Simons 2n plus 1. Okay. Then you just commutator over, literally commutator delta 1 delta C2 acts on this guy. So therefore this one is literally delta C1 delta C2 acts on omega 2n plus 1 Chern-Simons. So this equation makes sense. So this equation tells you that there exists some omega Chern-Simons 2n plus 1 form. We call it Chern-Simons form. We'll see why it's called Chern-Simons form. Like this way, they exist. Okay, and since the if you apply okay, and then if you define and we define I to n plus 2 form as just exterior derivative of omega to n plus 1 Chern-Simons form. So we define. This is define 2n plus 2 form. It's just exterior derivative of the 2n plus 1 Chern-Simons form. And this is the important quantity because I mean so what are the property? So property of I to n plus 2. First of all, di to n plus 2 is equal to what? 0, because I mean dd square dd is equal to 0. Another thing is delta whatever delta b I to n plus 2 is equal to delta b d omega Chern-Simons 2n plus 1 2n plus 1. Okay, let me go to 2n plus 1 and then since delta b is a gauge transformation and the d is exterior derivative, so this should commute. So therefore d delta b omega Chern-Simons to n plus 1. And if you look at that upstairs over there, sorry, I think I should mention that this is it depends on C. Sorry, I should mention since it's we specify the direction of the Lie derivative of omega. So this omega Chern-Simons itself is independent of C. But if you act on the C direction, the Beer-Series transformation, you get this is the dependence of C. And then this one is equal to, so from here, what would you get is the, what was that? D squared omega 2n. D squared omega 2n. and this is equal to 0. Okay? This is equal to 0. So this means that this is the closed form, and this means gauge invariant. Okay. So this is the property for 2n plus 2 dimensional. Okay. So people call this is an anomaly polynomial. No, why it's called an anomaly polynomial is become the evident from the Duke-Hose. So Duke-Hose. But let me move on. So far, what we have learned is what? Starting from I to n plus 2, which is closed, and then gauge invariant, invariant, 2n plus 2 form, and which satisfy the following condition. So I to n plus 2 is locally written by the exterior derivative or Chern-Simons of 2n plus 1 form. And if you take the gauge variation of the Chern-Simons of 2n plus 1 form, you get the exterior derivative of 2n form. And then, so far. And then from here, one can get the effective action, gauge transformation effective action is indeed 2 pi times m to space-time direction omega to n c direction. So that's what we have done. Or more precisely, just if you don't specify b, you just make this. So this is the anomaly. So this is anomaly. And furthermore, so what we have learned is the West-Zumino consistency condition. Guarantees that this one is equal to gauge transformation acts on square is equal to twice is equal to 0. Okay. So starting from this, you just construct I to n plus 2. Closed gauge. I mean, you don't need to take a picture because it's recorded. So you can. The video is available. So this starting from this action. So this depends on the theory. So the theory. So especially dimension of the space-time, and also matter content, Carl Fermi, the content of Carl Fermi. Okay. Starting from this gauge invariant close to n plus 2, you solve this equation, which is called descent equation. So this is called descent equation. And you obtain omega to n. And if you apply, if you integrate over this omega to n, you get the anomaly. And this descent equation can be written as diagrammatic way. So diagrammatic way. It starts from I to n plus 2, and if you apply d omega Chern-Simons of 2n plus 1, and if you delta b, you get 0. But if you apply delta b, you get the d omega to n. Okay, and if you apply delta b again, you get the 0. And then if you apply d again, omega to n, then and then delta B, you get the some form omega d to n minus 1 and d, and then some d omega to n minus 1 and so. So the arithmetic way of writing this descent equation is like this way. So it's just omega to n plus 1. This is the some nice feature of the it's called anomaly polynomial. I'm going to explain this one. Now since the d square equals 0, delta b square is equal to 0, so you get this kind of diagram. And what's important is this omega to n to get the anomaly. So that's the meaning of the descent equation, diagrammatic way of understanding of the descent equation. Okay. So let's give you some examples. So those are all the some abstract so this is the Stora Zimino descent equation. So now let's move on. Okay, so let's give an example. So the most important, if you ask the mathematicians, what is the closed engaging parent to n plus 2 form, most likely people will tell you that this is the most fundamental. It's called Chan class of n plus 1 of f. So f is ADA, dA plus S square. It's just usually a form of curvature or field strength of gauge field, whatever you call it. And this is defined as the follows. I to my notation is like this way. Maybe like this way, n plus 1 factorial over trace of I times f 2 pi n plus 1. Now f takes the value of this Lie algebra. Yeah, so it's a matrix value form. And they just take the some appropriate number of the coefficient and take the power is just the multiplication as a matrix multiplication, and then take a trace. So this is called Chan character. So this is called Chan character. Chan character. Anyway, I now understand the Chen. Character Chan. No, character is not. This is Chan class, but this is Chan character. Anyway, I don't know how to write a character. Anyway, most likely my guess is like this way. Is it correct? In Japanese, this is the case. In Japanese, this is the case. Anyway, where are we? So this is, as you can easily see, gauge invariant is guaranteed because trace is the already, so this is the case. So it's a, if you want to take a trace, it's gauge invariant, and the df is equal to 0 because of Bianchi identity. So it's closed form. So now how do you find a Chern-Simons form? For instance, f is given by 1/8 pi square and trace of f square. Okay. So and then to get the d omega Chern-Simons. So this is which form? what is the form as an exterior derivative? What's the degree of the exterior derivative? Which form? What is the degree of the as an exterior derivative? So manifold, you can integrate, so this is a differential form. So you can integrate this one in the some manifold. Which dimension of the manifold you should integrate over? What's the dimension? What? Yeah, 4, because I mean it's f wedge f. F is a 2 form. F wedge f is 4 form. It has to be 4 manifold. It's a 4 manifold. So this is Chern-Simons term is 3, and then this has to be equal to 1/8 pi squared trace of a f minus 1/3 a cube. Okay. So if you take the d axon here, you get the trace f squared. So be careful, this is not 2/3 a cube. Okay? What I'm talking about? Oh, sorry. It's not the plus, sorry. It's not the plus. It's not plus 1/3. If it is plus 1/3, this is indeed trace of a dA plus 2/3. It's okay. Sorry. It's a cube. Oh, it's okay. It's totally fine. It's a Chern-Simons term. Yeah, it should be Chern-Simons, right? Yeah, it's Chern-Simons term. Yeah. So this is indeed. Sorry, I mean, why do I write this one? So I should write down the ADA plus 2/3 a cube. Yeah, of course, that's true. So that's why it's called the origin. And then Chern-Simons, if you start with the sleeve of this one, is minus I48 pi squared trace of f cube, and then omega Chern-Simons, it should be 5, and this is equal to some number, and then trace of a f squared minus 1/2 a cube f plus 1/10 a 5, like this. And so, anyway, so this is the origin why it's called a Chern-Simons form, and so on. So for higher dimension, there's a way to get the there's a way to get the Chern-Simons form, but I'm not going to explain. It's written in the lecture note. I'm not going to go into detail. It's just example. And how to get the, so let's see. So delta omega 3 Chern-Simons B has to be omega 2. Okay? D omega 2, sorry. Omega 2. And then it turns out that if you do the honest computation, you will get as follows. The omega 2 is equal to, it's kind of annoying to write down. I think I only write down, in the case of UN gauge group, in the case of G is equal to UN, I wrote the general form expression. I didn't write down explicitly omega 2 case in this case. I don't know how to, I cannot do it by immediately now. I think, let me think. Can I do the, I see. So the omega 2 is most likely the form, no, I don't think I can do that. Sorry, I don't think I can do that at this moment. I don't know how. Can I do it? No, I don't think I can do at this moment. Okay, so for general expression, 2n expression is written in the lecture note. You can do that. I think if you solve this one explicitly, you won't get obtain omega 2n. I'm not gonna do that. Okay, so I don't want to waste your time. Because I mean, this one should be related to what's zoom in action, and then to get the zoom in action from d omega 2. Yeah, it's better not to do it at this moment. Anyway, so that's how you obtain. I mean, anyway, so there's a method to obtain omega 2n to compute an anomaly. So that's the case. Compute an anomaly. So let's move on. So far we only talk about the d mu is something like a partial mu plus a mu psi x on psi plus chiral ferment. As if mu is a connection of the bundle or like a H field of the field, the whatever. But if the M2N is a curve manifold with a different with curvature, so this will just move to sublet it into the following form. Psi plus, this is called spin connection. Essentially, this plays the role of Christoffel symbol. Christoffel symbol in spinor bundle or spinor bundle of the ferment. Okay, so essentially, Christoffel symbol is different. So in this case, the anomaly I 2n plus 1, 2 is as follows. So I mentioned that this depends on the theory, and it's called anomaly polynomial. The reason why is that it's as follows. So I 2n plus 2 is some polynomial. It depends on trace of R square. R is the, anyway, I will explain. Trace of R n plus 1, n or plus 1, and then trace of f, trace of f n plus 1. So those were, so namely, so this is a polynomial, means a polynomial. Polynomial sum over ck trace of r to k times trace of f n plus 1 minus 2k. Okay, so that's what's going to happen. K runs from 0 to whatever. N plus 1 over 2. Ck is some real coefficient. So here R is the curvature of the spin connection. So R is actually RAB is the omega AB plus omega AC omega CB. So this is the curvature of the spin connection. And then F is, as you know, dA plus A wedge A. So this is a Riemannian curvature, essentially. This is a Riemannian curvature. And this is field strength. And if you take some power and take trace, you get some form, and it just product means wedge product, and then if you multiply some coefficient and sum over. Okay, that's why it's called anomaly polynomial. So that's why it's called anomaly polynomial. It's because it takes a polynomial form with respect to variable trace of curvature times trace of curve. And the reason, and here I start with trace of f, okay? Trace of f. it can be non-zero. But here, trace of R square. I didn't consider trace of R. Okay? And I actually, I put the bracket here. And here, K, R to the power is always even here. Okay? Even here. The reason is the form. This curvature form, RAB, curvature form, indeed is the curvature of the space-time T, the curvature of the connection of the space-time to n plus 2 or whatever. It should be n plus 2, yes. But anyway, n plus 2 plus 2. Yes, I think it should be n plus 2. But anyway, so here it's just coming from the holonomy. Yes. T n plus 2. And the holonomy of this one is indeed SO to n plus 2. So therefore, always this one can be written like this way. You can take the following the basis of the of AB. Okay, so this is indeed the SO 2n plus 2, the algebra. SO, the algebra. So which is antisymmetric. So this means that if you do the, as you know, if antisymmetric matrix just multiply odd number, trace of R to the 2k plus 1. So if you multiply antisymmetric matrix with an odd number, it's still antisymmetric. So and if you take a trace, it should be 0. As you can see, the trace of R is just looking at the only 0. So therefore, it should be 0. Okay. If you only diagonal part is 0. The same thing happens once you multiply the odd number of times. So therefore, trace of R to the odd is always 0. So that's why I only include the even power here. Okay, so that's the case. And I'm not sure if I can go to the anomaly cancellation, but let me give you the flavor of how to compute I to n plus 1. So example anomaly polynomial. So this is just an example of the Chern class. Okay. Okay. So we know what is the fermion in the supergravity? Fermion of supergravity. Okay, supergravity. Here, so what we have encountered is type 2A is 8B cross 8, plus 8S cross 8B plus 8C. Type 2B is 8B plus 8S plus 8B plus 8S. And from here, so always NS Ramond, and Ramond and S sector will give you the fermions. And for here you have a dilatino, both plus minus, whatever, mu alpha, whatever. So this is dilatino, so this is spin 1/2, and a spin 3/2. Okay, so this the spinor indices will show up here like this way. But here you have only chiral, 2 copy, 2 times lambda plus, I don't remember the notation I had for me, like this. 2 copy of this. So this is the dilatino and the gravitino, okay? So it's a superpart of the dilaton and a superpart of the graviton. Okay, so since you have a plus and minus is a chirality, left-handed spinor in space-time, and right-hand spinor. So this is both has a plus and minus. So therefore it's non-chiral theory. Both plus and minus, left and right-handed. But here you only have the one part of the fermion, right? So only plus or only minus for graviton. So this means that it's chiral theory. It's a chiral theory in terms of fermion. In the viewpoint of from the viewpoint space-time fermion. But in terms of space-time fermion. In previously, this is the non-chiral theory in terms of worldsheet viewpoint. Okay. Worldsheet viewpoint left moving. Okay, holomorphic set and right anti-holomorphic. If you swap it, it's invariant. Okay. Worldsheet viewpoint. This is non-chiral. This is chiral. Okay. From the viewpoint of the worldsheet, because if you swap holomorphic anti-holomorphic S and C. Oh, sorry. This is 8. S and C will be swapped. Left and right will be exchanged. Okay. Worldsheet viewpoint, this is chiral theory, but from space-time viewpoint, space-time fermion viewpoint, the 2A is the non-chiral, because if you swap plus and minus, the theory does not change. But here, it clearly changes. Okay, plus goes to minus, minus goes to plus. The theory, the fermion will change. So in other words, it only has either left fermion or right chiral fermion. So therefore, it can have an anomaly. Okay. Type 1 is the, sorry, this is 8. So type 1 is just oriented for projection in terms of worldsheet viewpoint. You just identify the holomorphic and anti-holomorphic sector. So that at the end of the day, this 2 times this one is just to become lambda plus and psi minus mu. 1 copy. It becomes 1 copy. So for 2B, so you have a 2 copy of this guy, dilatino and gravitino. But in the case of the type 1, you only have 1 copy of them. However, type 1, we have a gaugino. I call it eta mu. Gaugino, whatever. I don't remember the chirality. So this is gaugino. Gaugino and gaugino. Yeah. So this is also can be involved. So what is the point of the this counting a few? So this is spin 1/2, and this is spin 3/2. So for gravitino, these fermions couple only the curvature. Okay, a space-time curvature, R. But this guy can couple both R and F. F is a field strength of gauge field. Because this is gauging. It's a superpolar gauge field. gauge field is mu. It's a superpart of the gauge field. Okay, superpart of gauge field. So therefore, it can be charged under the gauge field, but these are it can be charged under spin, only spin connection. Did I erase? Yeah, only spin connection. Okay, only spin connection, not gauge field. Okay, so that's that. Okay, and then we will compute the anomaly polynomial for these spin 1/2 and spin 3/2. To do that, I need to introduce some notation of the characteristic classes. So I'm not going to go into the detail. I mean, if you do the honest computation, you have to involve so-called index theorem. So we have to really use the index theorem to compute this anomalous polynomial. But I'm not going to go into the detail of index theorem. But I just give you this. So we learn chunk character of the whatever. N plus 1 f, which is the whatever 1 over n plus 1 factorial. What was that? Trace of I times f 2 pi n plus 1. So another thing is the so-called, so this is the associated so-called complex line bundle, or anyway, I'm not going to go into detail. Complex line bundle. But for real bundle, so this is SO2n plus 2. This is real bundle. Here there is so-called corresponding. This is churn character, and it's almost similar term time. So churn. This is 19. I forgot 44-ish. Anyway, when he was the IIS, he introduced this characteristic classes. And then there's a Russian Pontryagin introduced the real bundle, which is the P of R is given by as follows. Historical reason products of xi. Xi is this I, xi. And then this can be written 1 plus P1R plus P2R plus total, and so on. Pn R. I think sorry, xi squared. Sorry, xi squared. Like this. I think this is kind of like a dimensional wise, it's not good. Anyway, so this is the foreign dimensional manifold. Okay. This is not good. But anyway, notation is not good. Let's go n. N. This n is different from this n. Okay. And this one, Pi of R, is indeed cohomology, is 4i's cohomology of the manifold. 4i's cohomology of the manifold N. Okay. Manifold. So this is called Pontryagin class. So this is also known as the gauge invariant, and the closed form. So those are essentially most important character classes in addition to the Stiefel-Wetling class. I'm not going to go into the Stiefel-Wetling class, but these two are very important. Okay. So, and historically, I don't know, the reason that actually these were, even though these are the, anyway, used for Pontryagin class, some due to historical is called channel root. It's called roots. These x are called the Chern roots. Actually, it's just a two form. These are two form because R itself is two form, so the xi should be two form. These are called Chern roots. Essentially, the Chern, notice that the f can be written diagonal form, x1, x2, x whatever, xm, and so on. So people just Chern notice that the f locally can be diagonalized like this way, diagonalized, and he called it these are roots. He called it these are roots. So it's called, but it's the same role for SO. So these are called Chern roots, and so on. And then for SO bundle, so one can just multiply this kind of stuff. The Chern roots, you can define the so-called Pontryagin number. Okay. So these are character classes. And then another important class is called, these are, these these classes appear in the 1940s. But 1950s, late 1950s, people just, whatever, big mathematicians like Hirzbruch, or Atiyah, and Singer, or Bott, and so on, notice that it's better to introduce another basis for character classes. For instance, a hat of R. So this is called, do you know how do you call this? People call, this hat is roof. So people call a roof genus. A roof genus. This appears in the index theorem, also index theorem of the Dirac operator that appear in the Atiyah single index theorem. But anyway, so this one can be written just as the product of M. A is equal to 1 xa over 2 sinh xa over 2. Again, these xa are the Chern root of this matrix, curvature. And this can be written, anyway, it's just different basis. This can be written everything in terms of Pontryagin class. It's a lecture note, it's written in explicit form. You have to really change the basis of this Chern roots. So it's not essential, but it's convenient to do this kind of version. Okay. I think it's okay. Yeah, and it's P1 is Pontryagin number. Okay. So therefore, this is 4 form, and this is 8 form, and so on. And the people computed the gravitational contribution to the anomaly polynomial is as follows. It is the A hat R. I just give you the ad hoc, but the ad hoc way. But this is the case. This is the case. So here, so this is this Pontryagin class and the Chern character and so on. So here you just have any degree. So this is 4 form, and this is 8 form, and this is 4m form. Even like a roof genus, you have a 4 form, 8 form, and so on. Dot, 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 dot. So therefore, if you multiply them together, so for instance, if you do that like this way, and e to the some power, right? So this means that the 1 plus e, what was that? It's just a Taylor expansion, trace of r over 2 plus 1 over 2 factorial trace of r square, square plus dot, dot, dot. 1 over q. This means trace of r over 2 to the 3 and so on. So this will give you 2 form, 4 form, and 6 form, and so on. And this means, so if you multiply them together, you get the infinite many form. But what you need to do is just restrict only a 2n plus 2 form. So, yeah. So that's what you need to do for, so spin, so this is a gravitational contribution. So 3 over 2 is actually the spin 3 halves. So essentially, you have to take the information only from 2n plus 2. Moreover, I 1/2 of R and F is given by a roof of R and then chunk of F. Okay, chunk of F. Sorry, I think I should write down like this. So this means the chunk of F is trace of e to the what was that? I times f over 2 pi. This is the definition. Okay. So this factorial literally means if you expand it as a Taylor expansion of e, you get the factorial, right? And the power is literally the Taylor expansion of this. So this is the definition. Okay, so this is the coupling for spin connection of the spin connection. And this is coupling for gauge field. Gauge field. So let's look at the type 2b. Type 2b, supergravity. Unfortunately, I erased the matter content. Type 2b, supergravity. If anomaly cancel or not. Anomaly cancel or not. I don't think I have a time to go to Green-Schwarz mechanism today. Maybe at the beginning of lecture I will explain. Because also I found a lot of typo in the lecture notes. No. But let me move on. Type 2b, you have 12 form. So d is equal to 10. D equal to 10. So this is 2n, 2 times 5. So the anomaly polynomial is the 10 plus 2. Okay? So two-dimensional higher form. Because of the descent equation, you have to find I12. So I12 3/2. So you just restrict yourself to n is equal to 5 and just do the computation and you look at the only 12 form. And what you'll end up with the following extremely complicated number. 967,680 31 p1 cubed minus 40. Sorry, I think this is 1/2. 1/2. Sorry, then 3/2. Let's start with 3/2. Sorry. 1/107,520 is crazy number. 25 p1 cubed minus 180. Excuse me. p1 p2 plus 880 p3. Okay. Now. So this is contribution psi minus mu. Okay? Psi minus mu, gravitational contribution. And how about the lambda plus? This is a Diratino contribution. Diratino only couple, so it is spin 1/2 and 12 form. But now it's not coupled to gauge field. We don't put that like a space filling plane on type 2b. We just do not introduce D-brane. It just only consider cross string and consider Diratino. So therefore, there is no gauge field. Okay, only spin connection is available. So we only look at the 12 form from A-roof genus. So and that will give you what was that? -1. 967,680 31 p1 cubed 44 44 p1 p2 plus 16 p cubed. It's a crazy number again, and there's no way to cancel. There's no way to cancel. And here comes the ingenuity of Albert's government Witten, most likely Witten. Witten noticed that, yeah, there's another chiral field in the type 2b. Another chiral field is actually self-deal form. Self-deal, whatever, 4 form or 5 form. C4 plus in the self-deal field, whose curvature we call G5, and G5 will satisfy the self-duality condition. Well, this is associated D3 brane. D3 brane. So this is indeed odd dimensional form. So therefore, it's another parity transformation. Parity is the, for instance, x0 to x10. So one of the field should be coordinate is the swapped under like this one, 2 to 9. One of the field is swapped on negative sign. Then this will be get the parity odd. So therefore this will contribute another way, and they just find that this self-duality 12 of R is indeed given by a so-called. I'm not going to go into detail. So his book form, his book anomaly polynomial, which is something like this is. Anyway, if you tangent of XA is the channel root of the spin field, spin connection, spinor curvature, and of 12. And notice that this is equal to of 12 is equal to again crazy number. So this is what Witten and Albert's government found. Huge crazy number. I mean, people sometimes, as a physicist, even though it's a crazy number, you have to do the computation, this kind of computation. Even Witten do this kind of computation. Okay? So it's a crazy computation, but one has to do. And if you do that kind of crazy number, one has to eventually notice that the minus, I mean, it's really tedious, but one has to do. Otherwise, you cannot find something new. ST of R is equal to 0. If you sum this one and this one minus this one, it turns out that this is equal to 0. So that's the average government. I mean 83 Witten and then average government form. So it's anomaly free. So as you notice, I mean here, the plus and minus, sorry, I think I should take the opposite sign. So this plus and minus have a different character, left and right, okay? That will give you the sign difference here, okay? This sign difference is indeed coming from the chirality of the Dilatino and then the Gravitino. And if you add the self-deal form of the anomaly polynomial, this is indeed 0. It looks a crazy number. It's a miraculous cancellation, therefore. Okay, it's a miraculous cancellation, and this is 0. And they're happy, very, very happy about it. And I just give you the flavor of the anomaly canceller type 1. Unfortunately, I don't have a time. Type 1 only look at the Gravitino and Gravitino and Gravitino chirality. So there's no longer self-deal form in type 1. Okay, type 1. And we can do the same computation. So minus I, what was it? 3/2 minus actually 1/2 plus and minus 1/2 of this one 12 form this is equal to 15120 cubed minus 13 P1 P2 plus 62 P3 is not zero. Okay, not zero. Even if you add plus, so plus this Gaugino contribution, Gaugino 1/2 of 12, and it's only depends on R here, and now Gaugino depends on gauge field F. What you get is as follows. It's a crazy computation. Churn class 6 ... and 10 plus 196 minus dmg divided by 960480 P3. So it's written in my lecture note, and they mostly not zero, not zero, and not zero. This is not zero. Okay, not zero. So that's what our experiment found. So type 1 is anomalous. That's what the people conclusion also written. Okay, and the next lecture, there's some magical cancellation occurs due to Green-Schwarz mechanism when G is equal to S plus 32 and E8 cross E8. Okay, let's stop here. So that's the beginning of the next lecture. Let's stop here.